Hi guys, so our physics video today is going to be expanding on the last video. So last time we talked about waves and this time we'll be discussing light waves. So what is a light wave? It's a more specific type of wave and they're considered to be electromagnetic. If you don't remember, electromagnetic waves do not require a medium, so they can travel in a medium such as air or water, but they can also travel in a vacuum or space. A constant that you're going to need to know for this unit is speed of light, which is equal to 3 times 10 to the 8th meters per second, and this is represented with the letter C. Now, recap from our last physics video, some wave characteristics you need to remember are wavelength, frequency, period, amplitude, and the speed equation for waves, which is velocity equals frequency times wavelength. Now, onto some new content. Basically, reflection is when light bounces off a surface and reflects. When you look at yourself in the mirror, you're seeing your reflection due to physics. There are two types of reflection. Regular reflection is when the incident rays of light hit a smooth surface and the reflected rays are parallel. So basically, everything is reflected neatly and there will be a clear reflected image. Diffuse reflection is when everything goes wrong, so the incident rays hit a rough surface, and the reflected rays go all different directions, so the reflected image is all messed up. The law of reflection says that when light bounces off a smooth surface, the angle of incidence is equal to the angle of reflection. So if the initial light ray hits the surface at 20 degrees, the reflected light ray will also be at an angle of 20 degrees. Total internal reflection follows the law of reflection. So this happens when angle of incidence equals angle of reflection. Now, refraction is different from reflection. Refraction is the bending of light as it passes from one medium to another, and this is due to change in speed. There are different types of mediums such as air, water, glass, etc., and they all have different densities, which causes the light to move either faster or slower. An example of refraction is if you put something like a pencil into a glass of water. The pencil will look weird and bent, and this is because of refraction. The top half of the pencil is in the air while the bottom half is in the water, so those two different mediums will cause refraction. Now, index of refraction, which is represented by the letter N, is an important part of this unit. So index of refraction is the ratio between speed of light in a vacuum and speed of light in a material. So speed of light in a vacuum, or C, is always equal to 3 times 10 to the 8th meters per second, but speed of light in a material, or V, depends on the material. So index of refraction helps us determine how much light is being bent or how much it's being slowed down in these different materials. Now, the formula for index of refraction is N equals C over V, and on the reference table, there's a whole table dedicated to the indexes of refraction for a bunch of different materials. Now, optical density is a concept you need to know. So this is basically how much a medium slows down the speed of light. So if a medium has a larger index of refraction, it is more dense, which causes light to move slower, and in turn, the light ray will bend towards the normal line. If the index of refraction of the medium is smaller, that means the medium is less dense and the light will move faster and will bend away from the normal. Also, the normal line is just an imaginary line that is drawn perpendicular to a surface to help show the angles of incidence and refraction. Okay, so now Snell's law is a formula that describes what happens when a ray of light goes from one medium to another. So the formula is N1 sine theta 1 equals N2 sine theta 2. N1 is the index of refraction in the first medium, sine theta 1 is sine of the initial angle, N2 is index of refraction in the second medium, and sine theta 2 is sine of the refracted angle. So usually in the Regents, they'll give you like the value of 3 of these things, and it'll make you solve for the missing one. Okay, now critical angle sometimes happens when light passes from a denser medium to a less dense medium. So the light can refract so much that it eventually hits 90 degrees, and once that happens, it will actually stay in the denser medium instead of passing into the less dense medium. So basically, critical angle is equal to angle of incidence, but only when angle of refraction equals 90 degrees. So critical angle is just angle of incidence, but that's only when angle of refraction is 90. Now, finally, moving on to diffraction, this is the bending of light or sound around a barrier. So basically, when the wave passes through a small opening, it will spread out and form a wide pattern. The pattern depends on a few different things like wavelength and width of the slit that the light passes through. So, for example, if there's a more narrow slit, that will lead to a wider pattern. Now, double slit diffraction is when light is shown through two slits instead of just one, and then the diffraction patterns interfere with each other. So this causes patterns of dark and bright areas called fringes, which are shown on a screen. Now, the formula for fringe spacing is wavelength over slit separation is equal to fringe separation over distance from slit to fringes. And this may seem super hard to memorize, but usually in a question they give you like 3 of these values and you have to solve for the 4th one. And you could just use your common sense to figure out which number corresponds to which thing. So now let's move on to some multiple choice practice. Number 1. The diagram below shows parallel rays of light incident on an irregular surface. Which phenomenon of light is illustrated by the diagram? So the first thing we should notice here is that these rays are all over the place. So this immediately tells us that this is diffuse reflection because this is definitely not going to form a clear image. Number 2. Base your answers to the following question on the diagram below, which represents two media with parallel surfaces in air and a ray of light passing through them. Compared to the speed of light in water, the speed of light in medium X is what? So we're looking at two mediums here, medium X and the water. At point F, we're going from medium X to the water, and we can see that the ray of light is bending away from the normal line once it reaches the water. So remember that when light bends away from the normal, that means it's entering a faster medium. So away equals faster. So that means that the light is faster in water than it is in medium X. So the speed of medium X is lower than the water. So this is choice A. Number 3, what is the speed of light in flint glass? So they tell us that the light is in flint glass and we need to find the speed of it. So we need to use the equation N equals C over V, because we can just get the index of refraction of flint glass from the reference table, and C is always 3 times 10 to the 8th meters per second. So we just plug everything in and solve for velocity. So index of refraction of flint glass is 1.66. That equals 3 times 10 to the 8th meters per second over velocity. And once we solve this out, we're going to get 1.81 times 10 to the 8th meters per second. The diagram below represents the interference pattern produced by a source of monochromatic light with a wavelength of 6 times 10 to the negative 7th meter. The light is incident upon two slits that are 2 times 10 to the negative 6 meter apart and 2 meters from the screen. Number 4. Distance x is equal to what? So whenever you see a question talking about distance and slits and stuff, automatically think of the equation wavelength over d equals x over L. And we need to find x, so let's plug in to solve for it. It tells us that wavelength equals 6 times 10 to the negative 7th meters. It tells us that d is 2 times 10 to the negative 6 meter. We need to solve for x, and it tells us that L is 2 meters. So once we solve for x, we're going to get 6 times 10 to the negative 1 meter. Number 5, the color of the incident light is what? So if we look at the reference table, you can notice that we can only find color through frequency. So we need to find the frequency of this light wave. It tells us the wavelength and it tells us the velocity because it doesn't specify a specific medium. So we can just use the speed of light in a vacuum. And we can put those two things into the formula V equals frequency times wavelength in order to solve for frequency. So our V, our velocity, is just going to be speed of light in a vacuum. So 3 times 10 to the 8th meters per second is equal to frequency times wavelength. The wavelength is 6 times 10 to the negative 7th meters. Okay, and now we solve for frequency. So frequency is 5 times 10 to the 14th. If we look at the reference table, this falls under the color orange. Number 6. If the distance between the slits and the screen is increased, then the distance x will what? So this question is just asking about the relationship in the formula. So let's write it out one more time. So wavelength over d equals x over L. So if we increase L, then we're going to have to also increase x in order to keep things proportional. So the answer is B, increase. Number 7, a light ray traveling in air enters a second medium and its speed slows down to 1.71 times 10 to the 8th meters per second. What is the absolute index of refraction of the second medium? So this is easy. It's asking for index of refraction, and it gives us speed in the medium, and speed of light in air or vacuum is constant. So we can just plug it into the formula, n equals c over v. So n equals 3 times 10 to the 8th meters per second over 1.71 times 10 to the 8th meters per second. And once we solve out for n, we're going to get 1.75. Number 8, how long will it take a light wave to travel a distance of 100 meters? So I'm not going to do any math for this question because you can solve it conceptually, which is easier. So this question says light wave. So we can just assume that's normal light in a vacuum, which travels at a speed of 3 times 10 to the 8th meters per second. So this ray of light travels 300 million meters within 1 second. If we're looking for the time that it takes to travel only 100 meters, then it's going to be much less time than 1 second. So the only reasonable choice we have here is going to be D, which is like a teeny tiny fraction of a second. Base your answers to questions 9 through 11 on the diagram below, which shows the top view of a double slit barrier. The distance between the slits D is 1 times 10 to the negative 3 meter. The barrier is illuminated with light whose wavelength is 6 times 10 to the negative 7 meter. An interference pattern is observed on the screen. So number 9, if light of a longer wavelength is used, distance x will what? So these questions seem like they're hard, but it's really not. So it's just asking for the relationships between different components in the formula. So this is like the same thing as question 6. So remember that the left side of the formula, so wavelength over D equals x over L. So the left side has to equal the right side. It has to stay proportional. So if wavelength increases, right, then x has to also increase in order to keep the ratio the same. And I'll use some numbers to show this. So I'm just going to make up some numbers to make things easier. So let's pretend that wavelength equals 8, right? Wavelength equals 8, D equals 2, x equals 4, and L equals 1. So 4 equals 4. This is equal, this is proportional, right? So if we increase wavelength, if we turn wavelength into 16, right? So now it's 16 over 2. 16 over 2 does not equal 4 over 1. We need to increase x and turn that into 8 in order to keep things proportional, okay? So that is why the answer is B. Number 10, if the distance L between the barrier and the screen is decreased, the distance x between the central maximum and the first maximum will what? So again, this is the same thing. So L decreases, then x has to decrease too in order to keep things proportional because it's wavelength over D equals x over L. So x over L, we're focusing on this, right? So let's pretend that x equals 16 and L equals 4, right? So 16 over 4 equals 4. So if L decreases and it turns into 2. 16 over 2 and 16 over 4 are not the same ratio. 16 needs to turn into 8 in order to keep things the same. And if L decreases, then x has to decrease as well. Number 11, if distance D between the slits is increased, distance x between the central maximum and the first maximum will what? So once again, we need to keep the ratio the same. So wavelength over D equals x over L. So if we increase D, what's going to happen to x is that it's going to decrease, right? So let's pretend that wavelength is 8, D is 4, x is 4, and L is 1, right? 2, right? So both sides are equal to 4. So if we increase D, right? So instead of 2, D is now 4, right? So 8 over 4 equals 4 over 1. That doesn't make sense. So you need to change x and decrease it to 2. So if D increases, then x has to decrease. So the answer is going to be choice A. Number 12, the diagram below represents shallow water waves of constant wavelength passing through two small openings A and B in a barrier. Which statement best describes the interference at point P? So at point P, It's the intersection of a crest and a trough, so this is destructive. It would be constructive if the point was at the intersection of two crests or two troughs, but a crest and a trough take away from each other, which causes destruction and loss of amplitude, which means the answer is going to be choice D. Number 13. In the diagram below, monochromatic light in air is about to travel through crown glass, water, and diamond. In which substance does the light travel the slowest? So it gives us all these materials, and we just need to look at the reference table to find their indexes of refraction. And so the largest N, or largest index of refraction, is going to make that's going to have the densest medium. So more dense means slower, so largest N means light travels slowest there. So crown glass is 1.52, water is 1.33, and diamond is 2.42. So the biggest one here is going to be diamond, which means our answer is diamond because it's the densest, so light is going to travel the slowest there. 14. Which characterizes a polarized wave? So a polarized wave only vibrates in one plane, while unpolarized waves are multiple planes. So the only choice here that says one plane is A, so our answer is going to be A. 15. Electromagnetic radiation having a wavelength of 1.3 times 10 to the negative 7 meter would be classified as what? So this question is similar to question 5, so we can assume that this electromagnetic radiation, aka a light wave, just has a speed of 3 times 10 to the 8th meters per second because that's the speed of light in a vacuum, and then we can use that plus the wavelength to solve for frequency. So V equals F lambda. So V is going to be 3 times 10 to the 8th meters per second equals frequency, what we're finding, and it gives us wavelength, so 1.3 times 10 to the negative 7 meter. And we solve for frequency, we're going to get 2.3 times 10 to the 15th. And when we look on the reference table, this is in the range of ultraviolet. This isn't even a color, so ultraviolet is our answer. 16. Base your answers to the following question on the diagram below, which represents a light ray traveling from air to lucite to medium Y and back into air. Light travels slowest in which material? So remember that a denser medium causes the light to move slower, and when this happens, the light bends towards the normal. So we're looking for the ray of light that's closest to the normal line, and the one that's closest is going to be medium Y. So our answer is B. 17. What occurs when light passes from water into flint glass? So all these answer choices are talking about speed, and the question is talking about water and flint glass, which means we need to take a look at their indexes of refraction, which we can find on the reference table. So water has an index of refraction of 1.33, and flint glass has an index of refraction of 1.66. So remember that the higher the index of refraction is, the denser the material is, and more dense means that light moves slower in it. So since flint has a larger index than water, the speed of light will decrease once it passes to the flint glass. So choices A and D are wrong because it's saying that speed will increase. So now, when the speed of a wave decreases, that's not going to affect frequency. Frequency stays the same, but the wave will travel slower, and as a result, the wavelength will decrease. So the answer is choice B. So because it's moving into a denser medium, which is the flint glass, the speed will decrease, the wavelength will become shorter, and frequency just stays the same. 18. The spreading of a wave into the region behind an obstruction is called what? So anytime you see a question talking about the spreading of a wave, immediately think diffraction. So our answer is C, diffraction. 19. The diagram below shows light rays in air about to strike a glass window. When the rays reach the boundary between the air and the glass, the light is what? So we can see that the light rays are in the air and then it hits a glass window. So the air is a different medium from the window. So once it hits the glass window, the light will refract. It won't refract fully though, because like when you look at yourself through a window, you could still see your reflection. That's common sense. So at that same time, some of the light is being reflected back into the air, which is why choice C is correct, as some of the light is being reflected and some is being refracted. 20. The diagram below represents a light ray reflecting from a plane mirror. So we can see here that this is a total internal reflection, which obeys the law of reflection. So initial angle equals refracted angle. So if this is 65, then this also has to be 65. So our answer is D, 65. 21. What happens to the frequency and the speed of an electromagnetic wave as it passes from air into glass? So this question is super similar to 17. So glass is obviously denser than air. So when the light passes from air to glass, it will slow down and frequency will be unaffected because frequency doesn't really matter here. So the answer is A. 22. In the diagram below, a monochromatic light ray is passing from medium A into medium B. The angle of incidence Q is varied by moving the light source S. When angle theta becomes the critical angle, the angle of refraction will be what? So this question talks about critical angle. So immediately we should remember that critical angle is equal to angle of incidence when angle of refraction equals 90 degrees. So the answer here is going to be 90 degrees. 23. A ray of light traveling in crown glass is incident on a diamond interface at an angle of 30 degrees, as shown in the diagram above. The angle of refraction for the light ray is closest to what? So this question gives us two mediums, the initial angle, and we have to solve for the refracted angle. So this is Snell's law. So I'm going to write out the formula and then plug everything in. So n1 sine theta 1 equals n2 sine theta 2 gives us n1. So crown glass, if we look on the reference table, that's 1.52. Sine 30 equals, so we can find this on the reference table as well. So diamond is 2.42 times sine theta 2. So once we solve this out, we can find that sine theta 2 is equal to around like 0.314, but that's obviously not our answer. We need to find the angle itself, so we're going to use inverse of sine to find that. So the actual angle alone is just going to be 18. So our answer is 18 degrees. 24. Compared to visible light, ultraviolet radiation is more harmful to human skin and eyes because ultraviolet radiation has a what? So if you go onto the reference table, you can see that ultraviolet radiation is to the left of visible light. So ultraviolet radiation is around 10 to the 15th or 10 to the 18th, while visible light is only 10 to the 14th. So ultraviolet radiation has a much higher frequency, which is what makes it more dangerous. So the answer is going to be D. 25. All frequencies of light have the same speed when traveling through a vacuum. So speed of light in a vacuum is always constant. It's always 3 times 10 to the 8th meters per second. If you put light in different mediums, its speed will change, but it will always be this value for light in a vacuum. 26. Which diagram below best represents the phenomenon of diffraction? So easy, diffraction is when light goes through a slit and then spreads out, and that's what A shows. 27. A straight glass rod appears to bend when placed in a beaker of water as shown in the diagram below. What is the best explanation for this phenomenon? So this one is also pretty easy. You can see that the light is being refracted as it is incident on the water because the glass rod looks like it's bending. So that is going to be choice D. Light is refracted as it crosses the air-water interface, which is like this area. Okay, 28. Light with a wavelength of 6 times 10 to the negative 7 meter passes through a pair of narrow slits and falls on a screen 2 meters away. If the distance between two adjacent bright bands on the screen is 3 times 10 to the negative 2 meter, what is the distance between the slits? So this question is talking about double slit diffraction, and it's asking us to find the distance between the slits. So we need to use the fringe separation formula. So wavelength over D equals X over L, and then we just plug in what we know and then solve for D. So Okay, so it tells us that wavelength is 6 times 10 to the negative 7 meter. We're solving for D. It tells us that X is 3 times 10 to the negative 2 meter, and that L is 2 meters. So once we solve for D, we're going to get 4 times 10 to the negative 5 meter. 29. Which phrase best describes the phenomenon illustrated by the diagram below? So, you could see that one ray of light is going in right here, and then there's multiple rays of light coming out. So, as they're coming out at different angles. So, this is refraction, and the white light is coming out as the visible light spectrum. So, it's going in as white light, and it's coming out as a bunch of different colors. So, this is also dispersion. So, the answer is going to be C. Refraction and dispersion. 30. The diagram below represents a group of light waves emitted simultaneously from a single source. The light waves would be classified as what? So these waves are synchronized and in phase with each other. You can see that because they're like, it's a nice pattern. So that means that they are monochromatic and coherent. If they weren't coherent or monochromatic, they would be like all over the place. So since they're all neat like this, that's how you know it's choice A. So let's move on to some short response now. So on the Regents exam, you're going to see a lot of short response like this. Almost every year, there's a short response question where you have to draw angle of refraction or like reflection or something. So for this one, let's see. So the diagram below represents a ray of light in flint glass incident on air at an angle of incidence of 30 degrees. Okay, so first question, calculate the angle of refraction of the light ray in the air. So it tells us the two materials, right, flint glass and air, and it tells us the angle of incidence, and we need to find angle of refraction. So what we need to do is use Snell's law for this. So N1 sine theta 1 equals N2 sine theta 2, right? And we just plug in. Flint glass is 1.66 sine 30. That equals not N2. It's 1.00, that's air, times sine theta 2. So once we do this, we can find that sine theta 2 is equal to 0.83, around that. We need to use inverse of sine in order to find the angle by itself. So just the angle is going to be 56 degrees. So that's our angle of refraction. Okay, so the next question is asking us to draw the refracted light ray on the diagram in the answer booklet. I'm just going to do it here. Alright, so this is going to be a little bit difficult for me because I'm on my iPad and I'm not really good at this. But basically, we just have to draw this out with the protractor. So we need to you have to place your protractor perpendicular to the normal line. So like right here, and then measure out 56 degrees because that's what we got for our angle of refraction. So 56 degrees, it should be somewhere around like here. So that should be 56 degrees. So now we have to draw our arrow, and then I'm just going to label it 56 degrees, and that's perfect. So last question for this one, state what happens to the wavelength of the light ray as the light ray passes into air from the flint glass. So this light ray is passing from flint glass to air. So it's going from a more dense medium to a less dense medium. This means that speed will increase. So the wavelength will also increase because frequency is staying constant and it's proportional. So basically speed increases, so wavelength will increase. And that's all you need for your answer. Base your answers to questions 81 through 85 on the information and diagram below. The diagram represents the path followed by a ray of light as it strikes a semicircular block of fused quartz perpendicular to its curved surface. So first thing we have to do is we have to use the protractor to determine the angle of incidence. So it already gives us the angle of incidence. It's right here. We just have to find out what it is. So we have to line this up and measure. Okay. We have to measure what it is. All right, so this is around like what? This is around like 28 degrees, something like that. So this is about 28 degrees. So the angle of incidence is 28 degrees. Now we have to calculate the angle of refraction as the light ray leaves the fused quartz at point O. So the light ray is going from fused quartz to air, and we just found the incident angle, so we just need to use Snell's law to find the angle of refraction again. So n1 sine theta 1 equals n2 sine theta 2. So the index of refraction of fused quartz is 1.46 times sine 28, and that equals n2, which is air, so just 1.00 times sine theta 2. So once again, we're going to get sine theta 2, and this is going to be around 0.685. We have to use inverse of sine to find the angle by itself. So just the angle is going to be 43 degrees. So that's going to be our angle of refraction. Now 84 is asking us to use the protractor to draw the refracted ray at the appropriate angle of refraction. All right, we just have to draw the refracted ray. Once again, I'm just going to take my protractor, line it up perpendicularly, and then measure out 43 degrees. Alright, so 43 degrees should look something like this. Remember to draw the arrow. I don't know what happened. My iPad's kind of like tweaking out. But that's all we have to do to draw the refracted ray. Now, the final question here is compare the frequency of the light in fused quartz to the frequency of the light in air. So a big thing about refraction is that it's very much dependent on speed of light in these different mediums. And because of that change in speed, wavelength also changes. However, frequency does not change at all. Refraction does nothing to frequency. So the frequency is going to stay the same in both mediums. Stays the same. And that's our final question for today.